Hi, my name is Dr. Hassan Muhyiddin. I'm a professor of electrical engineering at the Lums School of Science and Engineering. I'm extremely grateful to the organizers of M&M-2 Challenge, StackOn Workshop, and Mackay Conference for providing us with an opportunity to present our work. The title of our talk is Multi-View SALA-NET, which is a deep learning framework for simultaneous segmentation of right ventricle on multi-view cardiac MRI scans. The outline of my talk is as follows. I'll start by defining the problem and showcase the difficulties associated with the problem via a schematic description. I'll then expound on the proposed multi-view SALA-NET architecture and enumerate the experiments that we performed in order to establish the efficacy of the proposed approach. I'll round up my talk with results, conclusions, and future work. For more details, I strongly recommend my fellow scientists to look at our work, which is made publicly available at the following website. The problem that we are focusing on is the following. We want to come up with a fully automatic approach that generates accurate and robust segmentation of right ventricle on multi-phase, multi-view cardiac MRI scans. We focus on right ventricle segmentation because it forms the penultimate step towards non-invasive identification of RV-related pathologies, including dilated right ventricle, tricuspid regurgitation, and arrhythmogenesis. The imaging modality in question is magnetic resonance imaging, and we have access to multi-phase information in the form of volumetric scans at the end systolic and end diastolic cardiac phases. We also have access to multi-view information in the form of short axis and long axis scans. The clinical approach for segmentation of right ventricle is manual segmentation by expert cardiologists. Manual segmentation is well known to be costly and time intensive and suffers from high inter-rater and intra-rater variability. Automatic segmentation of right ventricle is challenging due to highly complex and variable shape of the right ventricle. On this slide, we can see that the shape of the right ventricle, which is the white region in the manual segmentation maps, has a high variability. And this variability is not only across patients, but also across cardiac phases. Moreover, accurate segmentation of right ventricle is further limited due to a poor identification of the basal plane in the short axis view. The identification of the basal plane is usually done in the long axis view, which makes it possible to isolate the right ventricle from the right atrium. To circumvent these limitations, we propose a multi-view SALA-NET framework that learns the complexity and the variability of the shape of the right ventricle via supervised learning, and a proper identification of the basal plane by exploiting complementary information from corresponding log axis scans. On this slide, we have the architecture of the proposed multi-view SALA-NET. It is a 2D architecture with an encoder-decoder backbone. It comprises of two branches, one for the short axis view and the other for the long axis view. The two encoding-decoding pathways are asymmetrical in the number of feature maps, which were manually optimized. The two pathways communicate at the root of the encoding pathway and exchange extremely rich set of synergistic features learned from short axis and long axis views. We also add deep supervision on the last three layers of the decoding pathway to improve upon gradient propagation and feature learning. In this slide, I have summarized the attributes that I just went over on the previous slide. In our experiments, we benefited from a publicly available dataset, the M&M-2 challenge. This challenge pools in datasets from 3 clinical centers from Spain, acquired with Siemens, Philips, and GE scanners. The dataset consists of 3 cohorts. The training cohort comprises of 160 subjects. The validation cohort comprises of 40 subjects. And the challenge cohort comprises of 160 subjects. Imaging data for each subject includes 3-dimensional MRI scans in the end diastolic and end systolic cardiac phases in short axis view, and 2-dimensional MRI scans in the end diastolic and end systolic cardiac phases in the long axis. We also have access to multi-class segmentation maps of the training cohort provided by expert cardiologists. M&M-2 dataset is also diverse in cardiac pathologies, as shown in this table. Of interest is the RV-related pathologies, dilated right ventricle, and tricuspidal regurgitation, which are not represented in the training cohort. These 60 subjects form the true set of generalizability of the proposed multi-view SALA net. In the spirit of reproducibility, this slide summarizes training and inference parameters used in our experiments. For more details, consult our paper. To establish the efficacy of the proposed approach, we performed the following experiments. In approach 1, we trained a non-holistic 2D unit for segmentation of right ventricle. 2 separate 2D units were trained, one for the short axis view and other for the long axis view. These 2 units are identical in the number of feature maps. In approach 2, we trained the multi-view SALA net without providing contextual information of the left ventricle. The model was trained to learn right ventricle label only, and no prior information on the left ventricle was included in the learning process. In approach 3, which is the proposed approach, we trained the multi-view SALA net with contextual information of the left ventricle. The model was trained to learn the left ventricle label and the right ventricle label. The left ventricle label acts as a spatial prior for RV segmentation, as the right ventricle is always left adjacent to the left ventricle, as depicted in this figure. This table summarizes quantitative results from our experiments. As shown on the training and validation cohorts, the proposed multi-view SALA net with LV context significantly outperformed competing methods in RV segmentation. We report the highest overall dice score and lowest Hausdorff metric for RV segmentation. It is important to note that the multi-view SALA net with considerably fewer parameters, i.e. 27.2 million, significantly outperformed non-holistic 2D unit, which has almost 39 million parameters. Our proposed approach consistently maintained its high performance on the challenge cohort, which was not made publicly available. We obtained an overall dice score of 90.66% on the challenge cohort and an overall Hausdorff of 10.40 millimeters. This table summarizes the performance of multi-view SALA net with LV context across 8 cardiac pathologies in the challenge cohort. Our proposed approach achieved superior segmentation performance on unseen RV-related pathologies, as shown in this bold font. For the dilated right ventricle and tricuspidal regurgitation, which comprised of 50 subjects in total, we obtained a consistently higher dice score in the short axis and long axis views, and a quite controlled Hausdorff distance in the short axis and long axis views. This slide shows predicted segmentation map of the right ventricle for a training subject. We see in the second and the third rows that non-holistic 2D unit model and multi-view SALA model without LV context under-segments the right ventricle in the basal and the mid-ventricular planes, as shown by these red arrows. However, the multi-view SALA model with LV context significantly improves segmentation of right ventricle in the basal and the mid-ventricular planes. And this is courtesy of synergistic feature sharing at the root of the encoder, as discussed previously. In conclusion, we learned that a holistic deep neural network, i.e. multi-view SALA net with LV context, can be trained to segment right ventricle on short axis and long axis views simultaneously. We also found that the complementary information from long axis view can improve upon the segmentation of RV in the basal and the mid-ventricular slices. We also demonstrated that the RV segmentation performance significantly improved if we incorporate contextual information of the left ventricle in the learning process. And finally, we demonstrated that the proposed model exhibits strong generalizability on novel RV pathologies, which were not represented in the training pool. There are a couple of limitations and future work that we have identified with our proposed method. In the proposed multi-view SALA-NET, we are training two parallel 2D unit architectures in a holistic way. In future work, we are going to explore if we can use a single unit architecture which can simultaneously segment short axis and long axis slices. Also, we focused on a 2D unit architecture instead of a 3D unit architecture. An interesting aspect would be to explore the efficacy of 3D unit architecture that exploits fully volumetric information and see if it leads to improved performance in RV segmentation. Finally, I would like to thank the grant from the Higher Education Commission of Pakistan that made this study possible. Thank you so much.